Okay, so now we're going to move on to this idea of rate of change, and gives a definition here. You need to be able to identify this. A function's rate of change is how a quantity is changing with respect to a change in another quantity. And the easy one to think about is your rate while you drive, miles per hour. How is the distance changing over a given time period? For nonlinear functions, the rate of change is not the same over an entire function, right? And so then, if you think of if we just had a line, the rate of change is constant here, right? It's up and over, up and over. It's the same up and over the whole time. But now they're saying, if it's a nonlinear function, if it's a nonlinear function, think of our parabolas that we've been talking about, right? The rate of change is changing the whole time, okay? But we can calculate the average rate of change, okay? And think about, driving down the road, driving from your house to school, right? It doesn't take the exact amount of time every time, right? Because sometimes maybe someone's in front of you going slower. Maybe you had to stop for the school bus or whatever. Someone's turning in front of you, things like that. Okay, but you can still calculate the average rate of time it takes you to get to school. What's the distance from your house to school and how long it took you to get there? That's the average rate of change. Okay, if you look at your speedometer, that would be an instantaneous rate of change. How fast are you going at that exact second you look down at the speedometer? Okay, and so now how do we find the average rate of change? Okay, and they talk about, they kind of describe what's going on, right? So the average rate of change of a function f of x is equal to the change in the value of the dependent variables f of b minus f of a. This is just your y values. Okay, divided by the change in the value of the independent variables b minus a. These are just your x values over the interval, right? This is a to b, including a and b. So whatever a is all the way to b, make sure you include those two endpoints. So really, we've seen this before. This is really just, this is the big deal, but this is really just the change in the y values over the change in the x values. Okay, and we've seen this before as slope, right? We usually mark that as m. So slope is just y2 minus y1 over x2 minus x1. Okay, so all we're talking about here is finding slope, but we're just not going to be on the line. We're going to just be between 2 points. Okay, so then down here, example 4. Determine the average rate of change of f of x, and they give us this function, negative x squared plus 2x minus 1 over the interval negative 4 to 4. Okay, so if we're matching it up to this up here, right, our a value is negative 4. So we'll put that there, and our b value is 4. And so then all we need to find is the y values that correspond with these. And we're going to do that by plugging them in. All right, so they have that here. Right, the average rate of change is equal to these two things subtracted, right? So 4 minus a negative 4, and f of 4 minus f of negative 4. And so then we got to find these y values. We've already been given the x values, so let's find the y values now. All right, so we find those by plugging them in. Watch your signs. When we evaluate this at 4, right, we get negative 16 here. If I can write it, negative 16. Let's not do it there. So right, it's negative 16 plus 8 minus 1. All right, so that's negative 8 minus 1 for negative 9. And then we're going to evaluate negative 4 doing the same way. We get negative 16 again at the first part. Now it's going to be minus 8 minus 1. So negative 16 minus 8, negative 24, negative 25. Okay, so now all we're doing is plugging it into our little, again, this is just the slope formula. So we're just going to plug it in here. Negative 9 minus a negative 25. Remember, that's negative 9 plus 25. So that would be 16 over 8 for 2. All right, so the average rate of change of the function over the interval negative 4 to 4 is 2. Okay, it could be 2 over 1. A lot of times it is going to be a fraction. Okay. I would suggest that you guys take a look at these checks, and we can take a look at those. But right, all you're going to do on this one, take negative 5, plug it in, take 5, plug it in, set up a slope formula. All right, so example 5 here, find average rate of change from a table. Okay, so this is exactly the same thing. The only difference is they've already computed out the values, and you should feel comfortable doing that on a calculator. This would be like, you can go to the table function on your graphing calculator, and it can produce something like this just for you. But we're going from negative 3 to 3. So here's negative 3, here's 3. Remember, we're finding the average rate of change. So that's simply the y values, the change in the y values over the change in the x values. All right, and so then they say, okay, well, what is f of 3? Well, f of 3 is down here. So negative 24. What's f of negative 3? Well, we're up here for 48. So negative 24 minus 48 is negative 72 over 6. And that simplifies to negative 12. So the average rate of change of the function over that interval is minus 12. Okay, and so, remember, this is a slope. So this is telling you that we're decreasing. Okay, so we started up higher. We started up higher and we're going lower, because that's what this negative is telling us. Okay, so this one's worth talking about, because I know one of the things that you're going to have to understand is that how to interpret these given a certain situation. It's not all going to be just numbers and plugging it in and here's a number. These things have real life applications. So the table shows the number of students who took the ACT between 2011 and 2015. Find the average rate of change in the number of students taking the ACT from these 2 years. Okay, so this is very straightforward. So we're looking at from 2011, so we need this information. This is going to be our y values, okay, and this is going to be our x values. 2015, these are the 2 places we need to know. Okay, so then in 2015, I'll start with that. There was 1,924,436. And we're going to take 1.6, or 1,623,112. Okay, and so 2015 to 2011. All right, so that numerator simplifies to 301,324. And then that's over a 4-year period. So when we simplify that further, we'll divide that by 4. Okay, and then we get 75,331. Okay, so now this is where units come in to play. They're very important, right? So the average rate of change is a positive 75,331 students per year. Okay, right? Because up here, this was students, and this was over 4 years. Okay, so notice that it is a positive, right? As a positive here. Okay, so what this is telling us, and we'll answer this question here in a second, is that every year on average, 75,331 more students took the ACT over this time period. Okay, so interpret your results in the context of the situation. So from 2011 to 2015, the number of students taking the ACT increased. Okay, and we know it's increasing, well, because it's a positive number, by an average of 75,331 students per year. All right, here's another one of these. So find the average rate of change from the graph. The graph shows the amount of money the United States has spent on sports footwear since 2005. Okay. So it only goes up to 2015, it looks like. Use the graph to estimate the average rate of change of spending on sports footwear. Okay, so the average rate of change, at one point you guys should have done like a scatter plot and then a line of best fit. So we're kind of doing a line of best fit here. Okay. So it says from the graph, the change in the y values is approximately 5.5, and the change in the x values is right. So then that's what we're looking for. So where does this 5.5 come from? Well, if you look right here, they're giving us this number here. Okay, so 5.72, and so we can call that basically 15.5 more or less. And then where does it end up? Well, here's the place where it ends up. So 20.99. I mean, that's basically 21. Okay, so think of our little formula where we're subtracting the y values. So 21 minus 15 and a half, right? That's about 5.5. And the change in the x values, well, we're going from 0 to 10. So then we know it's 10 years. So then the rate of change is approximately 5.5 over 10, or, right, we're going to reduce this. So we can divide by 5, so it'd be like 1.1 over 2, which is kind of a weird thing. I don't know how much of you guys remember this, but you'd move your decimal over in each place, so about 11 over 20. Okay, and what are these units here? So 11, no. Okay, so 11 is our y values, right? So spending in billions of dollars. Okay, so what we're saying is on average, and I don't know, maybe this isn't like, maybe this isn't exactly what we need. Maybe we got to divide by 10, because we're going over 20 years here. So like, right, it's increasing by $11 billion because we're in billions of dollars over a 20-year period. Okay, so maybe we want it per year, so we'd have to divide that out. So then that would be, this is probably what they want. They probably want this. So 0.55, right? 5.5 divided by 10. So then 0.55, so half a billion, this is in billions of dollars, so 0.55 is $500 million every year. Okay, so over here, right, they're getting more exact with it. So they say actually find out exactly what these numbers are, as opposed to just an estimate. So we're estimating it at about, $500 million. What is that? $550 million increase every year. Okay, that was our estimate from the previous page. And so now let's see exactly what it is. Okay, so then we get 5.27 over 10. Okay, and so then if we simplify that out, it'd be 0.527. Remember, this is in billions of dollars per year. Okay, so from 2000, what was it? From 2005 to 2015, the amount of money spent on sports footwear in the United States increased again, right? Increased because it's a positive by an average of 0.527. Good grief. $527 billion per year. Okay, and so you can see that our estimate is relatively close to the actual amount. And that's important. Depending on what you need, right? An estimate will do you just good. It's about $500 million per year increase. All right, so that should be able to take you all the way through the rest of this section up to 26. Okay, pretty much all you're doing is a slope formula.